Journal of Graph Theory and Application since 2013. And by her determination of doing research, she was acknowledged as one of the 100 outstanding women researchers, Indonesian National Committee for UNESCO and Indonesian Ministry of Women Empowerment in 2010. And she finished his bachelor degree in mathematics, ITB, in 1996, and her master degree in mathematics, ITB, 1998, and she got her PhD in computer science in University of Newcastle, Australia, in 2003. And before we start our class today, I will tell you some rules that we have. First, the speaker has around 2.5 hours to give talk, and the rest minutes will be the Q&A session. Second, the speaker can take break time anytime that she wants during the class. So, Ms. Rinovia, you can say to us if you want to have a break time during your class. And the last one, you can ask questions. The participant can ask questions during presentation by writing down your question in the chat box. But you can ask directly to Ms. Rinovia at the end of the class in our Q&A session. So maybe that's all. So let's start our class for today. Ms. Rinovia Simanjuntak, PhD, time is yours.
Okay, thank you, Maya, for a very kind introduction. And also thank you for the committee of the IVC 2022 that invited me to give a lecture, one of the lectures in this IVC 2022. So as mentioned before, I will talk about a brief introduction to graph theory. So basically, I will introduce you to what is graph and several parameters in the graph. And the parameters that I will discuss here, that I will focus my lecture in, will be the one that will be discussed in the other lectures presentation. Yeah. So for instance, with Dr. Sabto presentation, in Dr. Intan and also Dr. Nuning. Yeah. So some of the parameters that I will discuss today will be applied, yeah, in their lectures. And I will divide my lectures into two parts. The first one is more classical graph theory. And then the second part will be about contemporary graph theory. So the recent development in graph theory that we recently use for real world application. Okay, so let me share my slide. Okay. So slideshow, just a second, the network is a bit slow here. Okay, I think I need to swap the presentation. Okay, so can you see my slide clearly now? Yes?
Yes.
All right. So, as was introduced before, my name is Rinovia Simanjuntak. My email is there. So if you have any question, you can contact me through the email. So first of all, how many of you have already learned about graphs in your courses, maybe in high school or in the universities? Any of you? No? Well, okay, so sometimes I will ask questions, yeah? Okay, so Eugene, you have learned about graphs, right, before? Okay, and the others, probably majority of you haven't learned about graphs at all. Well, I see some of my students here, so they should raise their hand. All right. So basically, we have deal with a lot of graphs in our lives, yeah. But usually they call networks, yeah. So for instance, if we see Facebook, I think most of you are users of Facebooks or Twitter or Instagrams, yeah, or any social media. And you can imagine that each of you is a point, yeah, a point in the Facebook universe. And when you have a friend, then you will have a connection between the nodes that representing yourself and also your friends, yeah. So if we try to map the connection between Facebook points, yeah, it will look like this, yeah. It is not clear at all because this is a very small picture compared to the real networks of Facebook. This was drawn in 2010. So probably if we take today's data, it will be more dense than this graph that it's shown you here. Okay. Another network that we are familiar with is the internet. Yeah. So there is a very nice project by Barrett Lyon. Yeah, it's called the Opti project, and it tries to visualize the internet. Yes, from 1997 until 2021, yeah, until last year. So let's see the video here that. So it visualized the change, yeah, from 1997 until last year, the internet. Yeah, so now we are in 2007. So hopefully you can see the videos clearly. Servers, building data centers, all to make this work. The web is incredibly exciting because it is the fulfillment of a lot of our dreams. I think that the web is going to be profound what it does to our society. The internet is the largest engineering project the Earth has ever seen, and we're just getting started. Okay, so this is the current situation of the internet, the current map of the internet until last year, yeah, until 2021. It's a big network, of course, yeah, consisting of billions of nodes, yeah, and also billions of connections. Okay, but okay, maybe I have to. All right. So, but we also have other kind of networks. Yeah, for instance, we also have this protein to protein interaction that can be described or can be drawn as a network, yeah, or a graph, right? Later on, we will learn about the graph. Okay, so this is yeast. The Latin name is written there, yeah. I don't know how to pronounce it, so I rather not read it. But this is several different proteins. So you can see that there are 1,870 nodes, yeah, in the which represent each protein in the yeast, right? And you can see that there are 2,240 connections between those proteins, right? So this was published in Nature in 2001. And we also have other kind of network, yeah. So for instance, if we consider cancer therapy, yeah. So if we use immunotherapy for cancer, yeah, some of the patient do not respond to the therapy, yeah. So So a lot of scientists try to study why this happened. Yeah, so some patients respond to the therapy, some don't, right? So the effector response can also be drawn in a network. Yeah, you can see there is a small network here, right? This is a visualization of the effector response of a particle tumor. Yeah, this in this case, this is a breast tumor, a tumor in breast cancer. Okay, so you can see networks is everywhere. Yeah, so as long as we have two individuals with connection between them, we can represent them as networks, or mathematically, yeah, we can model them as graphs. So another example is pedestrian walk, for instance. Yeah, so we can have, so if we have a particular road, yeah, a particular road here where there are many houses or many shops or whatever. So you can see the nodes here, yeah, in each side of the street, yeah. We can also have a networks of these nodes with their connections, yeah. Connections, of course, representing the street or the road between any two nodes in these networks, yeah. Okay, so that's some example which shows us that networks is everywhere, yeah. And probably this is my last example. So this is a colorful network, yeah. So but what is it really? Yeah, so this is published in 2017 in a web page called Link Curious, and it is actually the network of organizations connected to Donald Trump, yeah. So anything, yeah, we can basically, if there is a connection, we can model them as network or as a graph. Okay, so but what is a graph really? Okay, so I said before that everything around us, there are a lot of network, yeah, around us, and this was also published in 2012 by Berg and Feltner, and they said that the world is basically a network. Okay, so this is a very brief history of graph theory. Yeah, I start with the classical graph theory. It started at 1768, yeah, by a gentleman called Leonhard Euler. So there is a city in Prussia, yeah, called Königsberg. Now it is part of Russia. Okay, so the city has what do you call this, piece of lands, yeah. There are 4 of them, yeah. I want to use the pointer, but then it becomes very slow, yeah. So the you can see a piece of land A, yeah, B, C, and D. Now it's getting slower. Okay, so probably I just stop the pointer. Okay, yeah. So A, B, C, and D, right? And there are 7 bridges connecting all this piece of land, yeah, because there are river, yeah, there are 2 rivers actually, which is called the Prigel River, passing through the town of Königsberg, right? Okay, so this is an original drawing of Euler, published in 1735, yeah, in a journal called Astronomy. Okay, so what is the question here? Yeah, the question is, could a citizen of the city take a walk through the town in such a way that each bridge would be crossed exactly once? Yeah, so for instance, a person starts in A, yeah, and then he crossed the bridge, one bridge into the land C, And then of course he has to go back to, I don't know, maybe to A or maybe to D, yeah. And then what this person wants is he wants to go through, yeah, the town, yeah, so passing all of the land, crossing each bridge exactly once, yeah. So at that time, Euler gave the solution that it is not possible to do so, yeah. And how he gave the solution is by representing the map of the Königsberg city into what we know called graph. Yeah, at the time he didn't call it graph. Yeah, so the name graph appear later on. So say this piece of land is represented by a node, yeah, or a vertex, right? So we have a vertex A, a vertex B, a vertex C, and a vertex D, right? And if there is a bridge connecting two of the vertices, then we have what we call edges, yeah. So we have connection between the two vertices, right? Okay, so we have two connection from A to C, yeah, one connection from A to D, one edge, two edges from A to B, another edge from B to D, and one more edge from C to D. Yeah, because we have all those bridges. Yeah, so altogether, 4 vertices and 7 edges, right? Okay, so how did Euler prove that it is not possible to do the walkthrough? Yeah, to walk through all the piece of lands of the of the city of Königsberg, passing the bridge exactly once. Yeah. So the reason is this. Yeah. So basically, if you want to go from A to C or from any piece of land, right? If you want to go there, yeah, you have one way, yeah, one way from A to C, right? But then if you want to go back to A, right, from anywhere, yeah, I don't know, maybe from C, the person already go to other places, yeah, and but then if we want to go to A, yeah, of course there will be another edge going through A, yeah. So in this case, we see that if we want to go through piece of lands and come back, yeah, there should be even number of edges, yeah, go through those particular vertex, right? Otherwise, it is not possible to do so, right? So in that case, if you want to go through a particular node, there should be edges, as there should be nodes, there should be vertices with even number of edges attached to them, right? But in this case, we can see that there are only odd number of edges, yeah, attached to each vertex, right? For instance, in A, there are 5, yeah, edges attached to the vertex A. In C3, in D3, in B, another 3, yeah. So there are no vertices with even number of what we call later degree. Yeah, I will go back to it. Yeah, with even number of edges attached to it, to the vertex. Yeah, in that case, we cannot do the walkabout. Yeah, passing all the bridges exactly once. Okay, so that's Euler reasoning. Yeah, not very difficult, I think, to see that it is not possible to do the question that were asked before. Okay, so this is the definition of a graph, yeah, formally. And this was, the name graph was introduced by Julius Peterson. Yeah, so some of you probably have learned about Peterson graphs. Yeah, if you have learned about graph theory before, you have heard about the Peterson graph. So this is the person who named this object as a graph. Yeah, so it was mentioned the first time in 1891. Yeah, so what is a graph? So graph is a pair of sets. Yeah, so we have a pair of sets, V and E, where V is the set of vertices and E is the set of edges connecting two vertices, right? Okay, so this is the definition of a graph. And I have a drawing of a graph here. You have, yeah, we have seen one before, yeah, in the representation of the Konigsberg city. So we have vertices, yeah, drawn as the dots here, yeah, and we also have edges connecting two vertices. Okay. Now I will move to two basic parameters, yeah, basic graph parameters that will appear frequently in the rest of my lecture, yeah, and I believe it will also appear in other lecturers presentation, yeah, later in this week or next week. Okay, so the first one is degree, yeah, of a vertex. The notation is this one, yeah, deg of V. Yeah, so what does it mean? It means the number of edges incident to V, right? So for instance, if I consider this vertex here, yeah, the one on the left, yeah, it has degree 3, yeah, because it has 3 edges incident to that particular vertex. While the other vertices, yeah, the vertices on the right, it has degree 1, yeah, because it has only one edge incident to the vertex, yeah. So if we go back to the Euler problem before, I have mentioned that the number of edges incident to a vertex is degree, yeah. So if we go back, then all of the vertices has to have even degree. Okay, so that's the first parameter. The second parameter is the distance between two vertices, yeah. So if I have two vertices U and V, so for instance, can you see my cursor here or not? Or should I use a pointer? So maybe I'll use a pen, yeah. So say this is U, yeah, and this is V, yeah. So the distance between the vertices U and V, or the notation is DUV, is the length of the shortest path, yeah. The shortest path, what is a path? That's path is just a sequence, yeah, of vertices and edges, yeah, alternatingly, yeah. So vertex H, yeah, such that we have, yeah, what look like flat, yeah. So yeah, I didn't define the path formally here, but I think you can understand what I meant with a path here, yeah. So for instance, we can see this path here, yeah. Okay, so this is of course the shortest path connecting U and V. Yeah, we can take other path. Yeah, for instance, if I want to go from here to here, yes, yeah, it's also connecting U and V, but that's not the shortest one. Yeah, so the length here, yeah, the lower path, yeah, is 2, yeah, because it passes 2 edges, right? Yeah. And the other one, the upper one, has length 3 because it passes 3 edges. Okay, so that's the distance, yeah, the definition of the distance. So you know 2 parameters of a graph. Yeah, the first one is the degree of a graph. The second one is the distance between two vertices. Sorry, the degree of a vertex and the distance between two vertices. Okay, so this is an example. Yeah. Who can answer this question? What is the degree of the blue vertex? The blue vertices, yeah, there are several of them. Someone answering? Okay, 5. Yeah. All right. Yeah, a lot of people answer 5. Yeah, that's true. Yeah, it's 5 because we can see that for the blue vertex, yeah, each of the blue vertex, it has 5 edges incident to it. Yeah. What about for the green one? Yeah, it is a regular graph. Yeah, thank you, Sultan. Okay, pointer on C. Okay. All right. Yeah, it's another 5. Yeah. Yeah, I think Ahmad already mentioned that it is a regular graph. Yeah, for those of you who are not familiar with the term regular graph, it means that all the vertices has the same degree. Yeah, you can see that the blue vertices has degree 5. Yeah, yeah, that's true. Thank you, Emilio. The red one also have degree 5. The green one, the yellow one is the same, has the same degree. So it is called a regular. Okay. So now I move to the distance. Yeah. What is the distance between two blue vertices? 1. Yeah, that's correct. Yeah, thank you. Yeah, a lot of you have answered. Okay, 1. Yeah, you can see that there is an edge connecting blue to blue vertices. It means that we have a path of length 1. Yeah. Okay. What about blue and green? Another one, right? Yep. Thank you. Thank you, Rian. Yeah, it's another one. Yeah. Blue and green, the distance is also 1. What about blue and red? 2. Yep, it's correct. Yeah. So if we want to go from a blue vertex to the red vertex, we have to pass the green vertex, right? So the distance is 2. All right. The last one, probably this is the last one. I don't know. So blue and yellow. Blue and yellow, it's 1. Yeah. Yeah, it is 1. Yeah, because it is adjacent to each other. Yeah, they are neighbors. Okay. So that's the basic parameters of degree and distance in a graph. Yeah. So there is an interesting fact about distance in real world network. So if we see our world, yeah, we can say it is a big world, right? Yeah. It has vast area, yeah, a lot of people inside, yeah, billion of them. So if we have a connection between people, yeah, so say I want to make a network between people, so where a person is a node, and if one person know another person, then there will be an edge between those two people. Yeah, so say I have that network, okay, but there is experiment, yeah, so this is based on experiment, yeah, so it's not analytically proved. Yeah, the first one is in 1967 by Professor Milgram from Harvard University. Yeah, so what he did, he sent 160 packages. Yeah, 160 packages from Omaha, Nebraska. Yeah, to not he sent, yeah, so he wanted to send 160 packages from Omaha, Nebraska to a particular person in Boston, Massachusetts. Yeah. So what he did, he distributed the 160 packages, yeah, to different people, 160 different people, and they have to send the package to the people they know, of course, right? To their acquaintances, yeah. So, and Professor Milgram wants to know how many steps, yeah, how many steps will it take for the package to reach the particular person that he want to send, yeah, in Boston. Okay, so he did this experiment with the 160 people, yeah. Some of the so what the people did, of course, they tried to shorten the steps, right? To have at least steps as possible. So for instance, if a person know another person in Boston, yeah, he or she will send it to that person, right? Because if it is also in Boston, hopefully it will already be closer to the intended person. Yeah. Okay. Okay, so this experiment was conducted, and some of the packages, of course, did not arrive to the intended person, but the one that arrives, yeah, the ones that arrive, it will take either 1, 2, or 3 steps, yeah. So only that many steps, yeah, needed, yeah. Even though the intended person is in a different city, yeah, with the senders, and all of the 160% people choose to conduct this experiment didn't know the intended person, right? So it's quite a small step, yeah. But again, this is only for 160 persons, so maybe that's a coincidence, I don't know, but it was already published in Sick Today, yeah, in 1967, this experimentation. Okay, so the same experiment was recreated in 2003 by Watts, yeah. This is a group of people, a group of researchers from Columbia University, but now they use email instead of package, yeah. So the one before they use post service, yeah, because they want to send packages, but now they use email, yeah. So the very same experiment, but now they use 48,000 senders, yeah. And there are 19 targets, yeah. So 19 different targets. So each senders, of course, get one target. And these 48,000 senders are chosen from more than 150 countries. Yeah. And the result of the experiment, yeah, the second experiment, is around 6. Yeah. So the maximum is 6. The maximum steps needed, yeah, to send the email, yeah. Yeah, so from one person, they send to another person to send another person. So 6 steps, that's the maximum steps that needed to reach the 19 targets, right? This is a bit more impressive because there are a lot of more data than the first experiment, right? And then it was recreated again in 2008, yeah, by a group of computer scientists from Stanford. They use Microsoft Messenger, yeah. So at that time, probably it is the one that was frequently used in the United States, yeah, Microsoft Messenger. And they have 240 million people, yeah, they have data for 240 million people in the Microsoft Messenger, and there are 30 billion conversation, yeah. So when two people converse with each other, we say there is an edge, yeah. So they want to know what is the average length of path, yeah, inside that network, yeah. So 240 million people with 30 billion conversation, and they make a model of a graph with 180 million nodes. Yeah, so some of the nodes were eliminated, and 1.3 billion undirected edges. Yeah, because some of the conversations, there are 30 billion conversations, but probably the conversation are between the same pair of person, right? So they eliminated those repeated conversation. Okay, and the result, yeah, for this network, the average path is 6.6. Yeah, so we have a very big world, a lot of people in it, but actually, if we see the network of knowing each other, yeah, it is a small network. Yeah, we don't need a lot of steps to go to other person. Yeah, in our friends network, not really friends network, maybe acquaintance network. Yeah. So for instance, what do you think my length of path will be to, I don't know, Joe Biden, probably? Yeah. So say I know a particular lecturer here in Met ITB, yeah, who was a rector in one of our ministers' university, right? So he knows this minister, yeah. So these ministers know our president, yeah. Our president know Joe Biden. So that's only 4 steps actually, yeah, if we want to consider, yeah. So except of course for some very remote area, yeah, where nobody goes out and so on. Yeah. But although it looks like a big world, yeah, the distance between 2 nodes is much less than the number of edges, the number of nodes, yeah, the number of nodes inside the network. Yeah, so in that case we have what we call a small world network, which was introduced by Dodds, Muhammad, and Watts in 2003. And you can see here there is a name of Pak Robi Muhammad, yeah, who is still a lecturer in the University of Indonesia. Okay, and this raised to the concept of 6 degrees of separation. What does it mean? It means that, yeah, in average, if we delete all the isolated groups of people, yeah, at most, yeah, it is conjectured, it is conjectured that at most we only need 6 steps to reach other people in this world, yeah, through our connection network. Okay, so that's an interesting fact about distance, yeah, in graph. Another concept that I want to discuss today is about centrality. Yeah, so this concept will appear in Dr. Sabto Wahyu Indratno talk. Yeah, he will use a lot of centrality. Yeah, in the applications of graph theory there. Okay, so what is the concept of centrality? It is a concept to identify the important vertices in graph. Yeah, in a graph, right? Okay, but of course you can say that, well, what do you mean by important, right? So each person has different view of what important in their lives, right? Yeah. So of course it is also the same here, right? Yeah. So where is it? Okay. Yeah. Each vertex could be important from a particular angle, depending how we define importance, right? Okay. So I will introduce you to 4 types of centrality. Yeah, so depends on this how we define this importance. Yeah. And the applications, of the decentrality will include in identifying the most influential person in a social network. So if you want to see in Twitter Indonesia, who is the most influential person? Maybe you can use the concept of centrality there. Okay, there are a lot of. Node, point, and vertex are the same. That's true. Okay, thank you, Sultan Ahmad. I didn't see the question before. What is the question actually? What is node? That's vertex. So sometimes we use vertex, sometimes we use node, sometimes we use point. But so probably I should use vertex more consistently because I define it in the beginning as vertex. But if you see node, it's a vertex. Okay. So what else? The application for the centrality. Key infrastructure nodes in the internet. Or maybe urban networks. What is the key infrastructure nodes? Is it the gas station? Is it the hospital? Is it the fire? What do you call it? We call it in Indonesia pemadam kebakaran. Fire station, probably. Or maybe if we consider what is changing our world today, the COVID-19 pandemic. Maybe one also to know where is the super spreaders of a particular disease, right? Or if we have a brain networks and we want to know what is the important node in our brain networks. The most important node in our brain networks. But of course, again, all the answer will depend on how we define the importance, right? Okay, let's see the first one. The first one is the degree centrality. So the importance here, is measured based on the degree. So you still remember what the definition of the degree before. So we define the importance of a vertex in a graph based on its degree. So why is that? Maybe because the vertex has a lot of degree, then it has a lot of friends. It has a lot of so if we talk about road networks, street networks, so it has a lot of connections to other places in the city. If it has a lot of degree, right? Because a lot of edges are incident with that vertex. So with degree centrality, we say the vertex with the most degree, is the most important vertex. Okay, so the higher the degree of the vertex, the more important it is in the graph, right? So the degree centrality, the parameter of degree centrality, we call it D, capital D, of V, is just equal to the degree of that vertex. So if we have this friend networks, so we have how many people here until J? No, okay, I don't know how many people here. And it shows the friendship, friendship between two nodes, two people represented by the vertices, right? Okay. All right. So which one has the largest degree? Which is the most important vertex in this network of friendship? A? Yeah, that's true. Okay, A has how many degrees? 7, right? The others has less. The other have less degree than A. Yeah. So if we use the degree centrality, yeah, the most important vertex will be A. Okay. Of course, yeah, it can be more than one most important vertex, yeah, in a network, yeah. So it is possible for two or more vertices to have the same degree, yeah. So we can have more than one most important vertex based on the degree centrality. Okay, and of course here, if you want to order, yeah, if you want to order the importance of each of the vertex, you can do so, yeah. So you start with the highest degree, yeah, up to the lowest degree. Yeah, you can order all the vertices here from A to K to L, probably, yeah, to L. No, M until M, yeah. You can try to order them based on the degree centrality. Okay, so that's the first type of centrality. The second one is, wait a second, it doesn't move. Okay, this one. What we call closeness centrality. Yeah. So this defines the importance of a vertex by how close it is to all other vertices in the graph. Yeah. Right. So a vertex is important when it is close, yeah, relatively close, of course, to all other vertices in the graph. Yeah. So how do we measure this parameter? Yeah. So how we measure the parameter is for each vertex, yeah, we sum all the distance between that vertex to all the other vertices in the graph, yeah, right? Yeah, we just sum all the distance between that particular vertex to all other vertices in the graph, right? So which one is better, yeah? The one that has small sum or large sum? If we want to see the importance of a vertex based on how close it is to other vertices in the graph. So yes, that is true. Thank you, Rian. Yeah, Mukdas. Yeah, the smaller is the better.
Yeah.
Okay, I think I was kicked off. Yeah.
Yeah.
I don't know what happened. So probably the network.
Yeah.
So where was I? Did I talk about closeness?
Yeah.
Closeness, okay.
Yeah.
Have I mentioned the formula?
Nope.
No,
You just
okay.
see when you talk
That's
about
when I was logged out, right? All right. So as I mentioned before, yeah, we define for each vertex, yeah, the sum of the distance between that vertex to all other vertices in the graph, right? So the formula, yeah, formally, mathematically, it looks like this. Yeah, we have a parameter called CV, yeah, which is the closeness centrality of a vertex V. And yeah, as it was mentioned before, I just add, yeah, all the distance between V to all other vertices, yeah, U And you can see here that U is not equal to V. Yeah, so all other vertices, not V itself. Yeah, we sum all of them up together. So if we go back to our previous example of friendship network, yeah, which vertex do you think is the most important one based on the closeness centrality? Is it also A? Yeah. If we use degree centrality, A is the most important vertex. Yeah. Okay, it's A again. Why is that? Yeah, if you do the counting, yeah, of course. Yeah, the distance, yeah, you can see the distance from A to all the vertices here. Wait, all the vertices here is 1, right? And also this one is 1, right? Yeah. And to the other 3 vertices is 2. Yeah. Yes, you're correct, Ryan. Yeah. The maximum distance from A to the other vertices is 2. Yeah. So either 1 or 2. Yeah. So we just have to add a bunch of 1. Yeah. 1, 1, 1, 1, 1 plus 3 times 2. Yeah. But for the other vertex, yeah. For the other vertex, the other vertices, here you can see there are distance 4, yeah, distance 3, and so on. And if you do the calculation, yeah, for each of the vertex, you can see that A will have the minimum CV, yeah, or CA, yeah, in this case. All right, so that's closeness centrality. Yeah, the third one is, oh, it doesn't want to move. Okay, what we call the betweenness centrality. Yeah, so from the name you can see, so it has to be between something, yeah, between 2 things. Yeah. Okay, so what does this parameter measure? Yeah, so this measure the importance of a vertex based on how many times it occurs in the shortest path between all pairs of vertices in a graph. Yeah, so I'll just read it again. Yeah, so this is based upon how many times it occurs, yeah, in the shortest path between all pairs of vertices in a graph. Yeah, so basically what this parameter set, or what this parameter measure is how often the vertex appear in the route, yeah, in the shortest route, the shortest path between 2 other vertices. Yeah, so probably this parameter will be important will be applicable in road networks, for instance. Yeah, so if you want to know which city will be passed frequently, yeah, by motorists, yeah, going from one city to another city. Yeah, so say if I want to go from Jakarta to Yogyakarta, if I have to pass Bandung, yeah, then Bandung is between, yeah. Bandung occurs in the shortest path between Jakarta and Yogyakarta. If, yeah, I say if. I don't know what is the real thing. But if I choose 2 different cities, maybe Bandung also occurs there. Yeah, so I don't know. Yeah, so that's how we measure the importance of a vertex in a network in what we call the betweenness centrality. Yeah. Okay. So if we go back to this network again, yeah. Which do you think is the most important vertex based on this parameter? Yeah, based on this betweenness centrality. Yeah? How many times it occurs in the shortest path between all pairs of vertices in the graph? Is it still A? Yeah, it is A again. Yeah, you can see from how the graph, yeah, is constructed here. Yeah, if you have learned about graph theory, A is a cut vertex. Yeah, so basically everything has to pass A. Yeah, so if I go from D to F, yeah, I have to pass A. That's the shortest path. If I want to go from G to C, I have to pass A. From anywhere to anywhere else, I need to pass A. Yeah, so A will appear in every shortest path between all the other vertices in the graph. Yeah, and of course, automatically, it will become the most important vertex in this network based on the between the central. Okay, but how we measure it? Yeah, of course, if we talk about mathematics, yeah, we have to have a parameter that measure this parameter qualitatively. Yeah, so this is how we measure the parameter. Yeah, so we call it BV. Yeah, between the centrality. So we have two parameters here. Yeah, the first one is PXY. Yeah, what is PXY? PXY is the number of shortest paths connecting vertices X and Y. Yeah. So for instance, if I want to see what is how many shortest path between E and L. Yeah. Yeah, I can see one is this one, right? I go from here, here to here. That's of length 1, 2, 3, 4, right? That's the shortest, I think, yeah, because if we use other path, it will be either the same length or larger length. Yeah. And the second one, shortest path is from here to here, and then we go here, and then we go here. Is the same? No, it's not. So this is not the shortest path, I'm sorry. Yeah, this is not the shortest path because this needs 4. But here, this is the shortest path because it needs only 3. Yeah. So in this case, there is only one shortest path. Yeah. But if we consider two different vertices, maybe we will have more than one shortest path. Yeah. It is possible to have more than one shortest path. Okay. So in this case, for P, so I'll just write it here. P from E to L, it is equal to 1, right? And then the second parameter is this one, yeah, PXVY. What is this? This is the number of shortest path connecting vertices X and Y. So the same as before, but it has to pass through V. Yeah, so there is a V in the middle of X and Y. So we have to pass V to reach Y from X. Yeah. So in this case, if I want to know what is the PEAL, it is also equal to 1, right? Because this path, yeah, actually will pass A. Yeah. So for one particular term, yeah. So if I see the PEAL over PEL, it will be 1. Yeah, 1/1. Yeah, and we do the same thing for every other vertices. Yeah. So for instance, I have to count the P, E to C. Yeah. And we have, of course, to count the PE, AC, and so on. Yeah. So we have to do this for all other pairs in the graph. Yeah. So everything has to be counted. Yeah. And later on, you can try to count what is the BV, what is the BA. Yeah. What is the parameter for BA? What is the value for BA? Sorry. Yeah. And of course, you can also count the parameter for other vertices in the graph. And you can see that the other vertices will have less value of B, yeah, compared to the value of BA. Yeah. So that's why it is going to be. Okay, Mukdas. Oh, do you have a question? Mukdas Fatima?
Yes, I'm not getting point P X V Y.
I'm sorry?
I'm not getting second point. P X V Y is the number of shortest paths connecting vertices. The second one.
I don't really hear you. I don't know. Can someone repeat the question for me? Or maybe you can write the question. So what I wanted to count is the number of shortest paths. So PXY is the number of shortest path connecting vertices X to Y. PXVY. Okay, PXVY. So PXVY here. Yeah, what does it mean? It means the number of shortest paths connecting vertices X and Y, but it has to pass through V. Yeah. So if I say PEAL, what does it mean? It means that I want to count the number of shortest path from E to L. This is the path, but it has to pass the vertex A. Yeah. So PAL is also equal to 1. Yes, okay. This is a different one. Yeah. This is the one equal to 1. I'll just erase this one. Okay. So maybe I give you a different example. So for instance, if I want to count B of F, for instance, yeah. If I want to count B of F, yeah, this is the betweenness parameter of vertex F. This one is the vertex F. Yeah. Yeah, I have to count a lot of pair of vertices, of course. Yeah, one of them is from A to I. From A to I, how many shortest path? Yeah, the shortest path is, yeah, the number of path. Yeah, it's the number of the path, not the length of the path. The number of shortest path. Okay, maybe I have to repeat again, yeah, the definition. Yeah, PXY, yeah, PX1 is the number of shortest paths connecting vertices X to Y. So if I say PEL, I want to count the number of shortest path between E and L. Yeah, of course, if I want to count the length of the shortest path between E and L, it is what? It is 3. Yeah, that's the length of the shortest path. Yeah, we have other path, but of course the length will be greater than that, right? Okay, so but how many shortest path we have? Yeah, only this one. Yeah, only this one. Okay. Yep. All right. Yeah. So the number of shortest path, not the distance. Yeah, because we want to know the ratio. Yeah, the ratio between the all the shortest path. Yeah, with the number of the number of shortest path passing a particular vertex, right? So that's what we want to know. Yeah. So we want to know the number of shortest path, not the length, because we want to find out what is the ratio, yeah, that particular shortest path will pass a particular vertex. Okay, yeah. So what did I say before? So I want to show from A to I, yeah, from A to I, the shortest path is only this one, right? This is the only shortest path from A to I. So again, P of AI is equal to 1. Yeah. But now if I ask what is PA BI. See, this is the shortest path. Yeah, there is only one. Or there is two actually. Sorry, I didn't see the other one. So there is another one, which is this one. Yeah, from A to I, we have this one, 1, 2, right? Yeah, so actually this is equal to 2. Is there another one? No, I think there are only 2. Yeah, the green part of length 1 and the blue part of length 2. Yeah, if I go through B here, the length will be 3, so it is not the shortest part. Yeah, okay, so PAI, we have 2 of them. And if I ask PABI, what does it mean? I want to know what is how many shortest path from A to I which pass the vertex B, right? Yeah, okay, it's gonna be 0. Yeah, that's correct. Thank you, Ryan. It's gonna be 0, yeah. Because yeah, there is a path connecting A to I passing B, but it's not the shortest path. Yeah, so it is 0. Yeah, so if you take this division between PAI over PI, it will be 0. Yeah, it will be 0. Okay. Yeah. So I want to ask you the same question that I asked before with the other parameter. So using this parameter, the most important vertex will have the maximum B or the minimum B? The maximum, correct. Yeah. Yeah, the maximum, yeah. The maximum one. If a vertex has the maximum parameter BV, then it is the most important vertex with between a centrality. Okay. Okay, so I hope you understand. Yeah. So you can see that, for instance, this particular vertex B, yeah, B here, yeah, yeah, a lot of shortest path will not this B, yeah, a lot of shortest path will not pass B, right? Yeah, so only several shortest path will pass B. So if you consider this BV, there will be a lot of 0 terms, yeah, because a lot of shortest path does not pass through B. Yeah, and it will have a small value of B. Yeah, you can try to count it later. Okay, so in here we try to find the maximum BV. Yeah. Okay. Now the last centrality is what we call the eigenvector centrality, or EVC. Yeah. So this measures the importance of a vertex in the graph. Yeah, here A is the most important. Yes. Yeah, that's correct, Fariha Jamal. Yeah, so you can see that everything, every shortest path will pass A. Yeah, every shortest path will pass A. So you can see all terms will equal to 1 actually. Yeah, I think it's 1. Yeah. So all terms will be 1. So you will have 1 plus 1 plus 1 plus 1, yeah, for every pair of X and Y. Yeah. I don't know how many pair here. Yeah, you can see how many so it's basically, what is that? This is up to L, yeah, or no, M, up to M. So M is what? 13, yeah. So 13 choose 2, yeah. That's how many pairs that we have. And yeah, so we have 1 in each term. Yeah, so it will have the maximum value of B. Okay. Right. Okay, we move to the other centrality. Yeah. So this measures the importance of a vertex in the graph as a function of the importance of its neighbors. Yeah. So if I know, if I am friend with an important person, yeah, then I will also become important, right? So this is what this centrality set basically, yeah. So it measures the importance of vertex in a graph as a function of the importance of its neighbors. Yeah. So if a vertex is connected to highly important vertex, yeah, then it will have a higher EVC score. Yeah, EVC is the eigenvector centrality. Yeah, compared, of course, to other vertex which is connected to lesser important vertices. Right? Okay, so this parameter is what is used for what is called the Google page rank. Yeah, so if you do Google search, yeah, and you can see the rank, how it is placed in your search. Yeah, so this is not including the one which is the advertisement. Yeah, so some page, yeah, some website paid Google, yeah, to be listed higher, yeah, in the search page. Yeah, but this is not. Yeah, this is the one that didn't what is that, didn't pay the advertisement to Google. Yeah, and they base the page rank, yeah, by this parameter, yeah, eigenvector centrality. But of course we have to consider that the graph being used is a directed graph. Yeah, we will consider directed graph later on, yeah, after this. Yeah, so not, so what we have learned until up to now is only undirected graphs. Okay, all right, so I will explain about the eigenvector centrality with an example. Yeah, so probably it will be easier for you to understand. So let's say that we have this network here. Yeah, so we have 5 vertices A, B, C, D, and E with these edges. Yeah, the connection. Okay, and then I also need one matrix. Yeah, connected to this graph, which is called the adjacency matrix. Yeah. So what does it mean? It means that I have, because here I have 5 vertices, then I will have a 5 by 5 matrix. Yeah. So in general, if I have a graph with n vertices, I will have an n by n matrix, right? And it is a 0 and 1 matrix. Yeah. So the entry of the matrix is only 0 and 1. And how we define that? So here I order the rows and the columns of the matrix based on the labels of the graphs. Yeah, so for instance, this is A, yeah, this is B, this is C, D, E, and also the same with the columns. Yeah, it has to be the same with the columns. Yeah, same order with the columns A, B, C, D, E. Yep. Okay. So now, because there is no H between A and A, yeah, we don't have H between A and A, then we give the entry here, yeah, as 0, yeah, because there is no H between A and A. But because we have edges between A and B, this one we have also between A and C, A and D, then we fill in the entries by 1. Yeah, so 1, 1, 1. So that represent an H between the corresponding row and column. Yeah, so corresponding vertices, yeah, in the row and columns. Okay, and there is no H between A and E, so we give 0 here, yeah, in this entry. Yeah. Okay, it's the same thing. Yeah, B, there's an H between B and A, so it is 1. There is no H between B and B, but there is an H between B and C, and so on and so forth. You can fill in all the entries in the adjacency matrix of the graph. Yeah. So you can see here that the diagonal is 0. Yeah, because we don't have what we call loops. Yeah, in the graph. Yeah. So what is a loop? Loop is an H between a particular vertex to itself. Yeah. So if we have something like this, then of course the diagonal entry will be 1, but we don't have it in this graph. So all the diagonal will be 0. And you can see that this adjacency matrix is a symmetric matrix. Yeah. Why is that? Because of course, if I have an H between A and B, yeah, there will be an H between B and A, right? Yeah, it's a symmetric relation. That's why the matrix is also, the adjacency matrix is also symmetric. Okay, so this is the adjacency matrix. So what shall we do with that? Okay, so now assume, yeah, so remember, yeah, here we want to measure the importance of a vertex based as a function of the importance of the neighbors. Yeah. Yeah. So if a vertex connected to highly important vertex, yeah, it will have higher score. Yeah. So of course, now we have to define what is how we measure the importance of the neighbors, right? So to make it easier, yeah, I measure the importance of the neighbor by the degree. Yeah, so use degree centrality for the importance of the neighbors. Yeah, yeah. The higher the degree of a vertex, the more important is in the graph. Yeah. So of course you remember the first centrality, the degree centrality, is defined by just the degree of the vertex. Yeah. So we can write the degree centrality for each vertex in this graph by using a vector v here. Yeah. So the entries are representing the degree centrality or the degree of the vertex in the graph. Yeah. So this is for A, B, C, D, and A. Yeah. You can see A has degree 3, B has degree 3, right? C has degree 2, D has degree 3, and E has degree 1. All right. So this is the degree of each vertex in the graph, yeah, which give us the importance of the vertices based on the degree. Yeah. So now if we multiply the vertex A with the degree factor V, the factor V. So I multiply this A with V, yeah. Yeah, I hope you still remember how to multiply a matrix with a vector, right? Or two matrices, yeah, with different sizes. Yeah, so I get this value, right? Yeah, so this one, yeah, I multiply this row, the first row, with the element of the vector, and I add them together, yeah, and I get the value 8. But what does it really count? Yeah, so you can see here, yeah, A is adjacent or has neighbor C. Yeah, so maybe with B first. Yeah, because so A is neighbors with B, right? So I have an entry 1 in here, right? Because A is adjacent to B. Yeah. So if I multiply with the value of the degree of B here, which is 3, yeah, I get 3, right? Because 1 times 3, right? Yeah, because this represent the adjacency of A and B, and this represent the degree of B, this one, right? And the same thing, yeah, because it is adjacent to C, yeah, I multiply 1 with the degree of C, yeah. Same with, I think I marked the wrong entry. The entry for B should be this one, yeah. So 1 times 3 is this one, yeah. The first one is 0 times 3, yeah. So what counted was 1 times 3. Okay, for C, again, this one 1 times 2, yeah. Because the adjacency exists, yeah. because they are adjacent, yeah, A and C, and this is the degree of C, and so on and so forth. And you can see that because because A and E is not adjacent, are not neighbors, then we don't multiply with the degree of E. Yeah. So what is this value 8 here? Yeah, this is basically just the sum of all the degrees of the neighbors of A, right? Yeah. So why do we sum with the degrees? Because that's the we have decided, yeah, to use the degree as the importance, yeah, for the neighbors. Okay, so we do for all, yeah. So basically, you can see here in the same graphs, yeah, it is written in the bracket the value of this factor here, yeah, the result factor of AV, yeah. So 8, 8, 7, 6, 7, and 3, yeah. So you can see here A and B has the maximum values, yeah. Why? Because it is adjacent to highly important vertices, yeah. What is highly important vertices? In this case, the vertices with large degree, yeah. So it is A is adjacent to B, which has degree 3, and also D, which has degree 3, right? And B is also adjacent to A and D. Both of them has degree 3, yeah. So those are highly important vertices, yeah, based on the degree, yeah. So these two has maximum entries. But if you can see here, E has the minimum entry. Yeah, why? Because it is only adjacent, only it's only adjacent to D, right? Yeah, so no other vertices. Yeah, of course, D is highly important. Yeah, it has high degree, but only with one of them. The others has more, right? So that's why this is the vertex E has the minimum entry, yeah, which which we can interpret as the less important vertex with this measure. Okay, so this is called DEVZ, yeah, the eigenvalue centrality score of the first iteration. Yeah, why is it the first iteration? Because we can do this repeatedly. Yeah, we can do the second iteration. What we do is we multiply again with A, yeah. So the result here, 8, 8, 6, 7, 3, yeah. This is the result, right? We multiply again with A, the adjacency matrix, yeah. We can do this again, and we get this value. So what is this value actually? Yeah, it's the same, right? It's similar, it's not the same, yeah. Why? Because here we multiply with this factor, which is what? Which is the result of the previous iteration, yeah. So this one counted the sum of the degree of the neighbors of a particular vertex, right? Yeah. So now we multiply again with this, yeah. So basically we sum, yeah. So for A, for instance, yeah, for A, what we sum is the value of C, B, and D, yeah, because they are neighbors of A, right? Yeah, so you can see here I multiply this with this. Yeah, that's for B, this is for C, and this is for D. And I sum them all together. Yeah, so basically I add up the results, yeah, which is the AVC score based on the neighbors. Yeah, right? So how do we get this AVC score of the first iteration? By considering the neighbors of, so for instance, for D, yeah, the efficiency score for D, this 1, 3. No, for E, yeah, for example, yeah, for E here, it's 3. Why? Because it is adjacent to vertex D, which has degree 3, right? Yeah. So this value here is counted based on the neighbors of E. right? Okay, but now it is used again in this calculation. So basically we see the neighbors of the neighbors, right? Yeah. Okay, so this is called the efficiency score of the second iteration. Yeah, and what it does basically, so if we see the efficiency score of the first iteration, it is just a function of the neighbor. In this case, because we define the importance with degree, we sum the degree of the neighbors. Yeah, but when it comes to the second iteration, we see that it is a function of the neighbors and also the neighbors' neighbors. Yeah, yeah, because here, for instance, if I want to, so here 1 is multiply 1 here is multiply with 7, right? Yeah, and 7 here for D, we got it from what? From A, from B, and from E. Yeah, so from the neighbors of D. Yeah, so now, yeah, we see the neighbors of the neighbors. Yeah, and of course we can continue this iteration. Yeah, yeah, and so higher iterations, yeah, we will give us EVC score, yeah, as a function of vertices of distance 1. So I hope you still remember, yeah, what is the distance. So if two vertices are neighbors of each other, the distance between those two vertices will be 1, yeah. The distance from a vertex to the neighbors of the neighbors will be 2, right, and so on. Yeah, so we will go through all of these distances. Yeah, so from distance 1, distance 2, distance 3, and so on. Yeah, and it will provide us with more global, yeah, global in terms of the networks, yeah, efficiency score for the vertex V. Yeah, so usually we iterate until the efficiency scores reach an equilibrium. What does it mean? It means that it doesn't change anymore. Yeah, so usually if we already iterate until the value of the largest distance in the graph, yeah, which we call diameter, yeah, but that's another thing. Yeah, so then we will reach the equilibrium, yeah, of the EVC score. Yeah, so what does it mean? It means if we multiply with A again, it will give us the same factor, yeah, the same results. So we better stop. Yeah. Okay, so that's how we get the eigenvalues centrality for effects. All right. Yeah. So which one is the most important here? Is it gonna be A again? A here in here? So if we see the first iteration, A and B is the most important. Yeah. If we see the second iteration, again, A and B is the most important, are the most important. Yeah, because they have the same maximum value. Yeah, A and B. Yeah, you can try the third iteration. Is it still going to be A and B, or will they be different? Yeah, you can try. And you can try where for this particular network, yeah, how many iterations should we stop? Yeah, how many iterations should we stop for this particular network? Yeah, where yeah, all the iteration will give us the same result. Yeah, or the iteration give us an equilibrium. How many iteration do you think? Yeah, and which practices do you think the most important in each iteration? Yeah, do you think it will stay the same for A and B? Yeah, or in some step it will change? Yeah, I don't know. You can try. All right, so A and B. Yeah, probably it's still A and B. Yeah, for third iteration and so on. Okay, so that's decentrality. Yeah, so you will see again these 4 parameters, yeah, in Pak Sabto lectures in, I think it's next week, yeah, I don't know. You can see them. It's about market analysis, yeah, using centrality. Okay. So any question up to here? Okay, no question? Okay, so most of the real world networks is more feasible to be modeled. Okay, there is a chat. Okay, yeah. If we use what we call a directed graph, yeah, because up to here, yeah, we only learn about undirected graph, yeah. So for instance, in Bu Intan lectures, yeah, about neural network, and also in Bu Nuning's lecture about what is that? Disease network, yeah. Yeah, they will use directed graph instead of an undirected graph that we have seen up to here. Yeah. So what is a directed graph? So a directed graph, sometimes we call it digraph, yeah, for short, is a graph in which the edges have direction. So now we have direction in the edges, yeah. So usually if we draw it, we indicate the direction in the edge by an arrow in the edge, yeah. So formally, yeah, mathematically, yeah. So if we have V and W vertices in the graph, yeah, an edge, yeah, what we have before, an edge is an unordered pair V and W, yeah. So this is just a set consists of V and V, yeah. So this is unordered. So you can see that V, W, so you can see here VW is the same with, yeah, because this is just a set, right? So that's how we draw, how we denote the undirected H. But for directed H, yeah, or sometimes we call it an arc, yeah, it is an ordered pair, yeah. So this is a vector, you can see, yeah, we use the notation of a vector, and of course VW is different with WV, yeah. Okay, yeah. So when we have an arc from V to W, yeah, VW here, we draw it as an arrow from V to W. So we have V here, we have W here, we have an arrow, yeah, from V to W. Okay. So this is some of the examples, yeah. So here we have a arc 1, 3, also 1, 2, yeah, and so on, yeah. And you can see here that it is possible to have a double arc, yeah, with different directions, yeah. But of course, if we have this 2 directions of an arc, we can change it into just undirected H, yeah, because undirected H means we have direction from 3 to 4 and 4 to 3, yeah, because it is the same thing, yeah. So we can change these 2 arcs with just one undirected H. This is also another example. Yeah, another example of a directed graphs. Yeah. Okay. So if in the undirected graph we have a degree, yeah, the degree parameter, yeah. Here we also have degree parameter, but we have what we call out degree. and in degree. Yeah. So we differ between the number of edges going in and going out. Yeah. So for example, if we see this vertex 8 here, yeah, we can see that there is only one arc going out from 8. Yeah. So in that case, the out degree of 8 is 1. Yeah. But what about the in degree? Yeah. We have two arcs, yeah, going into 8. So the in degree of 8 is 2. Yeah. So the notation that we use is usually this one, degree in degree, yeah, or maybe just in the, yeah. Or maybe I don't use the notation, yeah, because I don't know what notation that will be used by the other lectures. Yeah. So you just have to understand that for the directed graphs, we have out degree and in degree. What about the distance? Okay, the distance is the same, but now if we consider path between two vertices in a digraph, in a directed graphs, you have to consider the direction. Yeah. So for instance, if I go from 3 to 7, yeah, from 3 to 7 here, I couldn't do it because, okay, there is this one, and can we go that way? No, yeah, because it's a different direction. So can we go from 3 to 7? Is there a path connecting 3 to 7?
No.
Yes, which one?
No.
Maybe I'll just delete everything so you can see it clearly. So remember, it has to be a directed path. Yeah, what does it mean? Directed path means that the path has to have the same direction. Yeah, so it has to be like this. Yeah, we cannot have opposite direction in a path. So from T to 7, actually we cannot reach 7 from 3, right? Because if I go from here, yeah, the only way to go is to here, and then I cannot go anywhere else, right? It will stop at 9. Yeah, I cannot go to 7, right? There is no way to do it. Yeah, if I go from here 3 to 10, it will stop here because there is no arc going out from 10. Yeah, so there is no path between from 3 to 7. Yeah, from 3 to 7 there is no path. In that case, the distance between 3 and 7 is said to be infinity. Yeah, because we cannot reach 7 from 3. Okay. Yeah, but if we want to see from 5 to 10, for instance, yeah, there is a path here, this one, and then from here to here, this one here. So the length of the path is 2. Is that the shortest one? Yeah, that's the only one, so it should be the shortest. Yeah. So you can see here the distance between 3 and 7 is equal to infinity because we cannot reach 7 from 3, but the distance from 5 to 10 is equal to 2. Yeah. Okay. All right. Yeah. So now you know the degree parameter, yeah, the out degree, the in degree, in the directed graph, you know how to count the distance. Yeah. So what we have done before for the centrality parameters, yeah, we can also do in directed graphs. Yeah. But you just have to change, yeah. Like the degree centrality, yeah, we will have of degree and in degree, yeah, for directed graphs. For the betweenness, we see the number of the shortest path, right? Yeah. So this is how we do the shortest path in directed graphs. Yeah. So we can apply, yeah, the parameters, the centrality parameters, yeah, also for the directed graphs. Yeah. And remember, if we consider the eigenvalues centrality, we use the adjacency matrix of the graph, right? This is also the same. If you have a directed graph, we can also have the adjacency matrix, yeah. But of course, the matrix will not be symmetric, yeah. Why? Because if we have an arc from 3 to 8, for instance, yeah, in the second example, we don't have an arc from 8 to 3, yeah. So the adjacency matrix is not symmetric anymore. But how we count the EVC, yeah, for the first iteration, the second iteration, yeah, in the undirected graph can also be applied for undirected graph. But of course, we use an adjacency matrix which is not symmetric. Yeah, but we can do the same. All right. Is there a question after this? I think. Okay, yeah. So for a particular graph, yeah, not just in the directed graphs. In this example, I use directed graphs. We can also have what we call the incidence matrix, yeah. So not just adjacency matrix. This is what we call the incidence matrix. Incidence. Yeah. So what we have in the rows are the representations of the vertices, right? We have vertices A, B, C, D, the blue ones there. And here we have the representation in the columns. We have the representations of the edges, the arcs, not the edges, the arcs, right? So for instance, here A, yeah, with the vertex A with the arc 1, yeah, it is going out, yeah. So that's why we fill in the entry as 1, yeah, because it's going out, yeah. And the other thing, A and the edge, the arc 3, yeah, the arc 3, it's going in, yeah. So we put in -1 here. With arc 4, it's again going out, so we put 1 there, yeah. So that's how we define the incidence matrix of a graph. And we can do this for undirected graphs also. But of course, for undirected graph, we don't have -1 values, yeah, inside. Yeah, only 0 and 1. Okay, so that's the incidence matrix. All right, yeah. So sometimes, yeah, we call a digraph, yeah, where we have a source and a target as a network, yeah. So we have a source, yeah. So say the source is S, and we have a target. So basically from S, we want to reach S, yeah. And each arc here has a positive capacity of weight, yeah. It's called the capacity of each edge, yeah. So this is an example, yeah. So say V1 is the source, and our target is 4, yeah. And how to reach V4 from V1? Yeah, of course, we can use this directed path here. Yeah, and you can see each of the edge in the path has a capacity. Yeah, so probably if we consider this as a road network, yeah, the capacity of the edges represent the number of cars that can pass, yeah, in each particular time, yeah, maybe in thousands, yeah. So maybe 1,000 car, or maybe in hundreds, I don't know, yeah. So for a particular, maybe not cities, yeah, maybe just intersections, yeah, from one intersection to another intersections, the capacity is maybe 100 cars, yeah, in a particular time, yeah. So altogether, yeah, if we want to reach from intersection V1 to intersection V4, we have to pass the other two intersections, and the capacities will be constant, yeah, 100, 100, 100. Or we can also use this path here, yeah. This is the shortest path, yeah. But if we consider the capacity will be larger, yeah. So if we add the capacity here, this is going to be 8, this is going to be 3. So I don't know, yeah, it depends on the representation of the capacity of the or the weight, yeah. I don't know, yeah, depends on the application. Probably some applications require minimum, yeah, weights, or some applications will need higher weights or so on, yeah, and so forth, yeah. So but now this is going to be different, yeah, although going through the upper path, yeah, if we use the distance, it is the shortest one. But if we add the capacities, yeah, going through the lower path will give us a minimum capacities, yeah. So depends on the application, you can decide which way it is better, yeah, to reach V4 from V1. So this is what we call a network, yeah. So there is a source and a target, and we also have capacity or weights in the edges or in the arcs of the directed graphs. Okay, so I think we have finished the first part, yeah. The second part will be shorter, yeah, because it's only yeah, some kind of informations, yeah, a new knowledge for you about contemporary graph theory. Yeah, we have also we will also discuss random graphs. So I think we will have a short break, yeah, of 10 minutes, yeah, and we will be back. So what time is it, Maya?
2:49. Maybe we can go back at 3 p.m.
3 p.m. Okay. Yeah. So this is up to 3:30, right? The lecture?
Yeah.
Okay. Yeah. So I
yeah.
think the second part will be about half an hour. Okay. So we will be back at 3 p.m.
Okay. Thank you, Ms. Rinovia.
Okay. So if you have any question of what we have discussed so far, you can write your question in the chat. Yeah. And I will look into it later on.
Fakultas Matematika dan Ilmu Pengetahuan Alam Institut Teknologi Bandung atau disingkat FMIPA ITB merupakan fakultas yang menyediakan program studi berakreditasi unggul dan terbaik di Indonesia bagi mereka yang ingin mendalami pengetahuan di bidang kimia, fisika, astronomi, dan matematika. FMIPA ITB merupakan yang tertua dan terdepan di Indonesia di bidang matematika dan ilmu pengetahuan alam dengan reputasi yang sudah diakui secara nasional dan internasional. Sebanyak 20 program studi yang ditawarkan terakreditasi A atau unggul oleh Badan Akreditasi Nasional Perguruan Tinggi. Dan keempat program studi di tingkat sarjana mendapatkan akreditasi bergengsi secara internasional. Setiap tahun, FMIPA ITB mendidik lebih dari 2.300 siswa, baik di tingkat sarjana, S2 maupun S3. Dalam memberikan pengajaran berkualitas, dosen-dosen FMIPA ITB didukung oleh 16 kelompok keilmuan yang aktif melakukan berbagai penelitian. Kelompok keilmuan astronomi bertujuan untuk mengembangkan ilmu astronomi, astrofisika, ilmu luar angkasa, dan ilmu lain yang berhubungan dengan astronomi. 6 kelompok keilmuan fisika aktif melakukan riset tentang bumi dan sistem kompleksnya, tentang material-material yang ada di alam dan pemanfaatannya, tentang material magnet dan fotonik serta pengembangannya, dan banyak lagi lainnya. Di bidang kimia, 4 kelompok keilmuan secara produktif mencari temuan-temuan baru untuk pengembangan, penerapan, dan penyebarluasan ilmu kimia, serta penyelesaian berbagai masalah yang berkaitan dengan kimia di masyarakat. Begitu juga dengan 5 kelompok keilmuan matematika, di mana para dosen di dalamnya mendukung proses pembelajaran matematika, serta pengembangan dan penerapan matematika di dunia modern saat ini melalui penelitian mereka. Proses pembelajaran dan kegiatan riset di FMIPA ITB didukung oleh fasilitas-fasilitas mumpuni yang dimiliki oleh fakultas. Observatorium Boscha merupakan observatorium modern tertua di Indonesia dan Asia Tenggara, sehingga memiliki peran yang sangat penting di dunia dalam pengamatan dan eksplorasi benda-benda angkasa. Laboratorium Fisika Terpadu dan Laboratorium Kimia Terpadu di FMIPA ITB memungkinkan para peneliti dari kelompok keilmuan yang berbeda-beda untuk dapat mengakses berbagai peralatan penelitian di satu lokasi saja, yaitu di masing-masing laboratorium terpadu tersebut. FMIPA ITB memiliki deretan kontribusi nyata dalam memajukan ilmu pengetahuan yang dinikmati oleh mahasiswa, masyarakat, dan juga industri. Bagi mahasiswa, komitmen FMIPA ITB dalam mendukung mahasiswa memaksimalkan kompetensi ternyatakan melalui upaya untuk secara rutin mengirimkan mahasiswa ke ajang kompetisi internasional yang sangat bergengsi seperti Olimpiade Matematika.
FMIPA ITB memfasilitasi mahasiswa FMIPA untuk berkompetisi pada tingkat nasional maupun internasional. Fasilitas yang disediakan berupa pembinaan dan akomodasi yang meliputi biaya maupun tempat pelaksanaan. Pada tahun 2021, FMIPA mengirimkan 5 mahasiswa pada kompetisi matematika internasional IMC 2021 dan berhasil mendapatkan 2 emas, 2 perak, dan 1 honorable mention.
Bagi masyarakat, lewat kelompok-kelompok keilmuan, dosen giat menjalankan pengabdian masyarakat yang sangat membanggakan fakultas.
Observatorium Boscha bersama dengan program studi dan astronomi di FMIPA ITB agar konsep-konsep dasar sains yang berkenaan dengan astronomi itu dapat menjadi bagian dari hidup masyarakat yang terintegrasi. Observatorium Boscha dengan dukungan FMIPA bekerja sama dengan banyak pihak, bisa NGO, bisa industri, bisa korporasi, jadi ada banyak yang bekerja sama mendukung program pendidikan astronomi yang menyediakan sumber belajar yang tidak ada batasnya. Karena peran Observatorium Boscha dan astronomi di ITB di bawah FMIPA ini ada banyak sekali yang berhubungan langsung dengan masyarakat. Umpamanya saja pengamatan bulan baru, hilal, bagaimana hari-hari penting itu ditentukan. Banyak sekali kontribusi dari Observatorium Boscha.
Kami telah banyak kerjasama dengan berbagai instansi pemerintah pusat dan daerah, pihak swasta dan industri di dalam maupun luar negeri untuk memajukan pendidikan, penelitian, dan pengabdian masyarakat. Kita telah juga membuka layanan penggunaan alat lab bagi masyarakat luas, diantaranya SEM, Microcity, NMR, alat praktikum pengajaran, dan HPC yang ada di gedung BSCA, dan juga peralatan lain yang tersebar di gedung Prodi dan juga Observatorium Boscha. Dengan peralatan ini, kami telah memberikan pelayanan dalam bidang pendidikan, penelitian, dan industri. Kerjasama dalam bidang penyelenggaraan beasiswa pasca sarjana juga telah kita lakukan, diantaranya penyelenggaraan pendidikan S2 pengajaran bagi guru di Departemen Agama dan juga Provinsi Bangka Belitung, dan akan menyusul beberapa Pemda lainnya. S2 dalam bidang aktuaria untuk
Okay, it's already 3 p.m. So let us continue. Just a second, I have to. Okay, so can you see my slide now?
Yes, ma'am.
All right. Okay, so yeah, what you have learned, yeah, it's an introduction to what we call a classical graph theory. So basically, it can be seen as a deterministic object. Yeah, why? Because we have a fixed vertices. Yeah, we have also. So if we consider a particular graph, we have a fixed vertex. We have fixed vertices. We have also fixed edges. Yeah, for that particular graph, right? But actually, this is what Albert and what Barabasi wrote in his book, yeah, that real networks behave very distinct from traditional assumption of graph theory, yeah. So what's the difference, yeah? So real world network changes over time, yeah. So for instance, if we consider social networks, yeah, social relationships formed and ended, yeah. So maybe we gain new friends, maybe we lose old friends, and so on, yeah. And maybe this relationship can change abruptly, yeah, over time. Yeah. And also, if we talk about technological networks, yeah, so for instance, computer networks, yeah, or server networks, yeah, internet service networks, of course it can have additional nodes, yeah, it can have new servers, yeah, and so on. And of course, with the new servers, we also have new connections, yeah, new edges, right? And then biological networks can change due to evolution and environment, yeah. So for instance, if a particular node or a particular node represents a particular organism, yeah, that node can change, yeah, over time, yeah, in biological network, because evolution, yeah. So we see that if we have virus networks, for instance, yeah, a virus can change, yeah, over time, yeah, it can mutate, yeah, into different kind of virus, yeah. So the vertex itself can change, right? Not only we add new vertices or we delete edges, but we can also change, yeah, a particular vertex because there is an evolution or mutation and so on. Yeah, so this is the difference between classical graph theory and the real world networks, yeah. So yeah, sometimes it's difficult to find complete and this is also a real world network problem, yeah. Sometimes it is difficult to find complete information about a particular network. So for instance, if we want to know complete information about the internet network in the whole world, yeah, it's gonna be very difficult because it is a very large network, yeah. Probably we can get partial information, yeah. For instance, the network in a particular server, for instance, the Google server, yeah, maybe we can have a more complete information for that particular server, or maybe a particular universities, a particular cities, whatever. But to get the whole information for the whole world, probably it is very difficult. Yeah, so that's about the particular about the real world. Yeah. So how to study real world networks? Yeah, so that's why there is sometimes, yeah, people said there is a new branch, yeah, of, I don't know, mathematics or computer science, which is called the network science, yeah. And this is the research of complete networks and system, yeah. So this is Barabasi book, yeah, network science. If you are interested with this subject, you can try to read his book. It is a very good book. And I quoted one of his sentence, yeah, in the beginning there, yeah, it says that the real world network is behave very different with the classical graph theory. Okay, so this is the definition from the UN and the US National Research Council, yeah, in 2006. This is the study of networks, representations of physical, biological, or social phenomena, leading to predictive models of these phenomena. Yeah, so what is the objective to learn these networks is to give predictive models, yeah, of the phenomena. Okay, so it can be either telecommunication networks, computer networks, biological networks, and other also networks, which happens in the real world. Okay, so we start with graph theory. This is classical graph theory started by Euler in the 18th century, yeah. And then in 1959, yeah, Aders and Renyi, yeah, they define a different kind of graph, yeah, which combine the classical graph theory with probability theory, yeah, which is called the random graph theory, yeah. So Paul Aders and Alfred Renyi combine the concept of graph theory and probability theory, and hopefully this will get us closer to the model for the real world networks, yeah. Because if we use the classical graph theory that we have before, it is not a good model. So in the ER graph, yeah, so Aders and Renyi graph, the existence of an edge between two vertices has probability P, yeah. So now the existence of an edge is not deterministic anymore, yeah. So the graphs that we learned before, either it is undirected or directed, yeah, it is fixed, right? So if we have these graphs, yeah, we have fixed vertices, we have fixed edges. But now we have, okay, fixed vertices, but the existence of an edge between the vertices has a certain probability, yeah. Okay, so now we have this formula or equation, yeah. So if n is the number of vertices, p is the probability of the existence of an edge between two vertices, right? That I mentioned before. Z is the average degree, and then m is the number of edges. Then we have this relation, yeah. So what is the average degree? The average degree is just the number of vertices, yeah, -1, yeah, because we delete the vertex itself, yeah. So when we consider a one particular vertex, so we see other n-1 vertices, right? So there are other vertices, there are n-1 of them, yeah. And to each of them, we have probability P to have a connection, yeah, to have an edge, yeah, between my vertex and the other n-1 vertices, right? So then the average degree will be just the probability times the number of vertices -1, yeah, not myself. Okay, what about the number of edges? Yeah, of course, the number of edges will be the average degree, yeah. So P times n-1 times the number of vertices altogether, n, yeah. And then because we can have so an edge connect two vertices, right? So it is counted in both vertices. So we have to divide it with half, yeah. So it's gonna be just this one, yeah, n times z, actually, yeah, n times the average degree divided by 2, yeah. So we get this value here. Okay, so this was first published in 1959 by Ayados and Renyi. And this opened a whole new line of research, yeah, in graph theory, yeah. So now we are getting closer to the model of real-world network, although it is not really, yeah, it is not a perfect model either, the ER graph. Okay, yeah. So what is the problem? Yeah, one of the problem is this one, yeah. So we can have giant component in a random graph, yeah. So I just start this video, yeah. So usually we start with P equal to 0, yeah. When P equal to 0, of course, there is no edge between any two vertices, right? Yeah. So completely disconnected. And then as P increases, yeah, then we have more edges, right? And this happens up to when P is up to 1 over n, yeah. We have what we call tree, yeah. What is a tree? A tree is a graph where we don't have cycles, yeah. But now this is already over 1 over n. We have cycles, and we have a large component, yeah. And then when we pass particular critical point, we will get a connected giant component. What does it mean? The giant component means it will consist the majority of the vertices in a graph. Yeah, so the majority of the vertices in graph will be in the random graph as the probability P is getting larger than the critical point PC, yeah, which already been counted as this value, yeah, so ln n over n, yeah. So this is the critical point, yeah. So when it already passed this value, then we will have a giant component in the random. All right, so that's actually is a problem, right? Because in real world networks, this is rarely ever happen, right? Yeah, we have a giant component. Maybe we have clusters of components, yeah. So maybe, for instance, for internet networks, yeah, we have clusters for Google's, yeah, clusters for I don't know what, Yahoo, maybe, yeah, clusters for Facebook, yeah. There is one cluster, not all together in the whole world we have one giant component. It is not possible, right? Yeah, for the internet networks. Yeah. So that's why another model appear, yeah, from Duncan Watts and Strogatz. Yeah, this is Watts and Strogatz, yeah, in 1998. Yeah, they introduce another random graph, yeah, but different with the different construction with what the Edwards and Renyi did. Yeah. So for Edwards and Renyi, what happened? They have fixed vertices, right? And then they add the edges based on a certain probability. Yeah. For Watson-Strogatz graphs or network, they start with what they call the lattice graph. Yeah. Or maybe if you have learned about graph theory, we call it circulant graphs here. Yeah. So this is a highly regular graphs. Yeah. This is so our first example is, yeah, one of example of the base graph of Watson-Strogatz network. Yeah. So this is a regular graphs. So how we connect? Yeah. So basically we do the jump. Yeah. So for instance, from here to here, jump 2. Yeah. So everything else jump 2, right? We also have jump 1. Yeah. So that's how we do it. Yeah. So this is the base graph, which is a circulant graph. And then what they did is they delayed half of the edges, connecting a particular vertex. Yeah. So maybe not half. Yeah. So maybe this will be easier for you to understand. So for instance, this we have these edges, right? We have this edge. Yeah. So this one can be deleted. Yeah. There is a probability for an edge to be deleted. Yeah. For instance, if we see this one is not deleted, right? So only this one and this one. Yeah. So there is a probability for it to be deleted. Yeah. And then originally there is an edge here, right? So we redirect, yeah, we redirect the edge here to here, for instance. Yeah. Yeah. So this deleted edge, which is deleted with a certain probability, will appear somewhere else with another with the same probability. Yeah. So probably here. Yeah. Okay. So what about this one here? Where does it go? It goes here. Yeah. Okay. Yeah. And we can increase the probability. Yeah. And we can get this one. Yeah. And so on. Yeah. And you can imagine. Yeah. Because what we do is we delay a particular edge. Yeah. And then we redirect. Yeah. We can it is possible for the network in some point becomes clusters, right? So for instance, all of these edges here are deleted. Yeah. So we have some clusters of connected components. Yeah. Clusters of components. Yeah. So we have connected components and then another connected components if we do this with increasing P. Yeah. So with the Watson-Strogatz networks, it is possible to have a local clustering. Yeah. Is it possible to have local clustering in the model, which is more close to what happened to the real world networks. Yeah. Because in real world networks, it is almost impossible to get the giant component like in the ER mode. Okay, so this is the Watson-Strogatz, yeah. But again, this network has deficiencies, yeah. It cannot really reflect the real world network, yeah. Until 1 year later, yeah. This is Barabasi and Albert, yeah. They propose another model. Yeah, I don't describe the model here. Yeah, but if you are interested with the model, you can search the internet or you can read Barabasi's book. Yeah, but actually, what I want to say here is that the network try to correct or try to add properties which are not appear in the other model or the other random networks from Edwards and Renyi and also Watts and Strogatz. Yeah. So what is the problem here? Maybe I'll just show you the graphs here, yeah. So this is what happened with the random networks, yeah. This is what happened with the random networks, yeah. So if we see the degree of the nodes, yeah, or the vertices, and this is the number of nodes, yeah. In the random networks, both in ER and in WS, yeah, Watson Strogatz, we have, it is almost this distributed, and yeah, the distribution is Poisson, yeah. So so what does it say? So if we have a lowly link degree, yeah, so this is small degrees, yeah. In here, small degrees. This is average degrees. This is high degree, right? Yeah. So the vertices with small degree, there are less of them, yeah. So we have a less number of nodes or of vertices with low degree, yeah. And then it goes up, yeah. So here, yeah, approximately in the middle, yeah, we have more number of vertices with this kind of degree here, yeah, the middle degree, right? The yeah, maybe we can say the average degree. And this is the very highly linked vertices, because they have high degree right here, and then they will go down again, yeah. But actually this phenomena does not reflect the real world networks, yeah, because the real world networks behave differently, like in the right hand side here, yeah. So for instance, if we consider internet networks, yeah, so most of the page or web page, yeah, they have, or maybe not internet, yeah, maybe say we have a friendship network, yeah. Yeah, so this degree, yeah, degree of the vertices represent the number of friends that a person have, right? Yeah. Okay, so a lot of people, yeah, this happened in the real network, yeah. A lot of people have less friends, right? Yeah, low number of friends, right? So a lot of people have less number of friends. And as we go through the degree of the vertices, yeah, if we go through here, yeah, here is the people with very high degree, right? So if you go to Twitter, for instance, maybe they have, I don't know, 3 million followers or whatever, yeah. And there are very few of them, right? Yeah, very few of them. So in real world networks, this phenomena in the left hand side of the graph doesn't occur frequently, yeah. So what we have is this kind of phenomena, yeah. This phenomena is called the scale free, yeah, the scale free characteristic, yeah. And it can be found in many real networks, yeah, biological spreading of disease, yeah, social networks, yeah, like I said before, maybe Twitter or Facebook, yeah. Maybe not Facebook, because it is the number of friends is limited, yeah, in Facebook. Maybe Twitter, yeah, because people can have millions and millions of followers there, yeah. And you can see there are very few of them, yeah, who are highly linked, right? So how to model this, yeah, because the other two models have this phenomena of the distribution of the node, but what we want is a model for the real networks where it behave in a scale-free characteristic, yeah. So and we can use the network, yeah, the construction of the network, which was proposed by Albert Berebesi and Albert, yeah. This was proposed in 1999, yeah. So this is already scale-free, and also already avoid the emergence of a giant component, yeah, for this model. Yeah, so nowadays, yeah, Barabasi and Albert model, or the modification of Barabasi and Albert model, are usually used for modeling scale-free networks. Yeah, so I think Bu Nuning will talk also about random scale-free network in her lecture next week. I don't know the schedule. Yeah, you can check this. Okay, so I think that's the end. Let me check whether probably I have some more news. Yeah, so if you are interested with big data science, yeah, this is some views, yeah, of several people, which is not graph series. Yeah, this is the view of computer scientists. Yeah, this is published in 2014. Yeah, they said that graph theory is the key to understanding big data. Yeah, and this was posed as a question, of course. Yeah, but because data has connection, yeah, there are connection between data, and probably understanding graph theory will give us more tools to understanding big data. Yeah, so we can let data connect itself. Yeah, and maybe if we do that, some meanings will emerge automatically. Yeah, this is also an article published in Science in 2016. Yeah, how we mine big data. Yeah, maybe it's better to see the network of data. Yeah, network of data. Yeah, and see the patterns in the network of data. Probably it is better than just considering simple descriptors. Yeah. Okay, so that's just something to think about. Yeah, if you want to work in that data science. And this is again a quote from Barabasi's book. Yeah, it says that we have taken apart the universe and we have no idea how to put it back together again, because we don't really know what is the connection between them. Yeah, and this is an old saying from Native American: with all things and in all things we are relatives. Yeah, so basically the world is just a big networks. Okay, I think that's all my lecture for today. So if you have any more question, you can ask. Otherwise, I hope you have copy my email address. Yeah, if you have question later on, you can send me an email. Okay, thank you.
Yeah, thank you so much, Ms. Rinovia, for your interesting lecture. And now we come to the Q&A session. So for you that already raised your hand before or have something to ask directly to Ms. Rinovia, you can ask her directly now. Is there any question?
Yes, some of the questions have been asked during the lecture.
Yeah.
But if you have more questions, you can ask.
So we have one question here. He sent me on direct message. I think it's a mistake. He asked about how to represent the discrete time dynamics of nodes value.
So the nodes has value that change over time. Is it correct?
Yeah.
Yeah. So basically, we have to give a function, yeah, to the nodes value, and so the nodes value will be a function of time, right? So what is the question actually? Because if you want to represent the value of a node where it is changing, yeah, then we just have to store, yeah. We have to have a function of over time, yeah, for the value of the nodes, yeah. So that's how we store it. So we have an evolution of the networks, yeah, over time, where the value of the node changes over time, yeah. So we just have a function of time, yeah, for the weight, yeah, or what we say before, yeah, the weight of the node, yeah.
Yeah, I think it's if there is a further question, you can ask it.
I hope it will answer your questions because. Yeah.
Okay, maybe while we are waiting for the another questions, maybe we can take a picture as documentation first.
Okay.
Okay. If you want to be show in this in the picture, you can turn on your camera first, and our operator will take screenshot or take the picture. Okay, I'll wait around 1 or 2 minutes for all of you to turn on your camera.
Yeah, I think most of you didn't open the camera, yeah.
Yeah. Please not. Can
Yeah.
you? Yeah.
Okay. I will count. 1, 2, 3. Okay, then the next slide. One, two, three. The next slide again. Okay, and the last slide. 1, 2, 3. Okay, thank you.
Okay. So, is there another questions? You can ask directly by raise your hand and open your mic, or if it is hard to ask Ms. Rinovia directly, you can write it on chat box. Or it seems like everyone already understand about your lecture.
Or probably they will have to think a bit more about it to ask questions. I don't know. Okay. Okay, you're welcome, Fariha.
Okay. So I'll give 2 last minutes if you have something in your mind to ask. Actually, we still have much time, around 15 to 20 minutes. So yeah, it will be good if you have questions that you can ask directly right now. Even you ask an email, maybe it will be, you will have late reply, but now you can ask Ms. Rinov directly.
Okay, some people express thank you. Yeah, so you're welcome, yeah, to all of you. Wahid Iqbal, Nur Fatima, Mukdas Fatima. Sorian, the question, it depends on the parameter of centrality. If it is the betweenness, then yeah, it is obvious that it will be the most important vertex. Yeah. If it is the degree, Probably not, yeah, because it can be the cut vertex has less degree than the other vertices, right? It's possible. Yeah. We can have, for instance, a path here, yeah. The vertex here is a cut vertex, but here we have a big subgraph here, right? So everything here has larger degree than the cut vertex itself, right? Yeah. Okay, so probably not that cut vertex, but maybe the other cut vertex. Yeah. So yeah, so you can try to figure out for each of the parameters of the centrality, yeah. But what is obvious, the cut vertex will be the most important vertex for the betweenness centrality. Yeah. So I think you have to think a bit more about the eigenvalue, yeah. Okay. Yeah, you're welcome, Rian. Okay, so will there be access to video recording later on, Maya?
Yes, in Sipendi, if I'm not mistaken.
Yeah.
We will have the recording. Okay, so
yeah, actually, because I have tried to download the previous lectures, the video lectures, and we don't have access. So
yeah, so maybe the access should be
maybe only for the organizers or not for the listeners, right?
Okay, maybe I'll ask Pak Rudy later.
Yeah, maybe the admin, yeah.
Yeah.
Yeah, you should ask them. So it's in YouTube or in Sipendi?
It should be in Sipendi, Bu.
In Sipendi, okay, yeah. So probably, yeah. So yeah, I will. I think Maya will pass this to the admin, yeah.
Yeah.
Okay.
Yeah, to correct the link.
Oh, okay. So I'll change my name to the admin so that I can have access.
Okay. Okay. About the recording, it will be handled by Mr. Rusdi as the admin. And if there is no other question, I think we should give virtual applause to the interesting lecture from Dr. Rinovia. And yeah, as the moderator, I want to say sorry if there is something mistake, if there is a mistake along this lecture. And thank you so much, and see you guys in the next class. Thank you, Dr. Rinovia, for the.
Thank you.